In July 2025, in Geneva, Switzerland, two detectors the size of apartment buildings recorded the same signal at the same fraction of a second. They were not coordinating. That is the entire point of the experimental design. ATLAS and CMS are built to operate independently. Separate instruments, separate teams, separate chains of data analysis. Precisely so that when both see the same thing at the same time, there is no reasonable way to attribute it to a calibration error or a software artifact. When both detectors agree, physics has to take the result seriously. The physicists monitoring the data looked at their screens for several minutes without speaking, not because something had malfunctioned, because the data showed a physical structure that, according to every calculation available, should not have had enough time to exist. The rules that physics uses to describe matter. The same rules that correctly predicted the behavior of particles to 10 decimal places for 50 years. Do not forbid this structure. They simply do not predict it. And this is not the first result like this to come out of the Large Hadron Collider in the past 3 years. Over the course of this video, we are going to work through what exactly appeared in that July dataset, and why it unsettled the people who spend their careers being unsurprised by data. We are going to look at a sequence of results from CERN's Run 3 that individually have explanations, and that together keep pointing in the same direction. We are going to look at what physics found that it was not looking for, and what it was looking for and could not find. And we are going to look at what the science is beginning to see at the end of that direction, and what it cannot yet put a name to. The Large Hadron Collider shuts down in 2026. This is what it leaves behind. The top quark is the heaviest elementary particle physics has ever confirmed. It weighs roughly as much as an entire atom of gold, packed into something with no measurable size at all, and it does not last. From the moment a top quark is produced in a collision, it has approximately 10 to the power of negative 25 seconds before it decays into lighter particles. That number is almost impossible to make intuitive. It is about 1 billion times faster than the timescale on which anything inside an atomic nucleus has a chance to interact with anything else. That timescale is the whole issue. For two particles to form a bound state, to hold together as a structure, they need time. They need to exchange the force carriers that create the bond. They need, in a very real physical sense, to feel each other. And the top quark, by every calculation that existed before July 2025, simply did not live long enough for that to happen. It decayed before the process could complete. A bound state of a top quark and its antimatter partner was not forbidden by the equations of quantum chromodynamics. It was considered physically out of reach at the energies the LHC operates at. Then, both ATLAS and CMS reported the same excess in their data. A statistical signal at the threshold energy for top quark pair production, matching the predicted signature of what physicists call Toponium, a fleeting quasi-bound state. The two heaviest known particles briefly holding together before both decay. The result crossed 5 sigma, the formal threshold for a discovery in particle physics. Considered experimentally unfeasible, then observed. That sequence matters. Not because it breaks anything, it does not technically, but because it tells us the calculation of what is reachable was wrong. And if it was wrong there, where else is it wrong? That is the question Run 3 keeps generating, not one dramatic rupture, a series of quiet places where the number does not land where it should. Every atom in every gram of matter anywhere on this planet holds together because of a set of equations physicists assembled between roughly 1960 and 1975. Those equations describe the behavior of elementary particles, how they interact, what forces they feel, what they can and cannot do. The framework is called the Standard Model of Particle Physics. That name honestly undersells it. It sounds like a working draft. It is not. It is the most precisely tested scientific theory in the history of human inquiry. Here is one number that makes that real. The electron's magnetic moment, a measure of how strongly it responds to a magnetic field, has been calculated using the standard model and then measured in the lab. The calculated value and the measured value agree to 11 decimal places. If that level of precision were applied to a measurement of the distance from New York to Los Angeles, the error would be smaller than the width of a human hair. That is the framework that the July 2025 result unsettles. Not breaks, unsettles. The standard model does not forbid Toponium. It just did not predict that the LHC would be able to produce it. The lifetime of the top quark was supposed to make it unreachable. The data said the calculation was off, and the honest reaction to that, at least the one I keep coming back to, is not panic. It is a more uncomfortable feeling. It is the feeling of realizing that a theory this precise, this repeatedly confirmed, this deeply embedded in our understanding of physical reality was wrong about something specific and measurable. What else is it wrong about that we have not measured yet? That question is not rhetorical. It is the actual working question in particle physics right now, in 2026. And Run 3 spent 3 years generating data that makes it sharper. To understand the weight of what is accumulating in the LHC data, it helps to be specific about what the standard model has actually done, not in general terms, in a list. In 1964, Peter Higgs and several colleagues proposed that a field permeating all of space was responsible for giving mass to elementary particles. The theory predicted a particle associated with that field. For 48 years, no experiment had the energy to find it. In 2012, Atlas and CMS announced its detection. The measured properties matched the theoretical prediction with a precision that represented the most accurate experimental confirmation in the history of particle physics at that moment. Before the Higgs, the W boson, predicted in the early 1970s, found at CERN in 1983. Before that, the gluon, the charm quark, the bottom quark, the top quark, each one predicted by the mathematics of the standard model years before any detector confirmed it. Each time, the theory was right. Each time, the number matched. This is what makes the current anomalies feel different from ordinary scientific noise. When a theory has been right about particle masses, interaction rates, and decay probabilities across 50 years and thousands of independent experiments, a deviation does not get dismissed because someone assumes the measurement is wrong. The W boson mass result in 2022 came in at 7 sigma. The muon anomaly has held above 4 sigma across multiple independent runs. These are not rounding errors in an imprecise theory. They are a precise theory being wrong in ways it has not been wrong before. There is a version of this story where each anomaly gets resolved individually. A calibration issue here, a theoretical correction there. Physics has seen that before, but there is another version, and the data keeps making it harder to ignore, where the anomalies are not separate problems, where they are the same problem showing up in different measurements. That version is the one the field is quietly sitting with right now. In April 2022, the CDF collaboration at Fermilab published the most precise measurement of the W boson mass ever recorded. The W boson is one of the force carriers of the weak nuclear force, the interaction responsible for certain types of radioactive decay and, among other things, for the nuclear processes that power stars. Its mass is a number the standard model predicts with high precision. The CDF result came in at 80,433 mega-electron volts. The standard model prediction sits at 80,357. The difference is 76 mega-electron volts. The statistical significance of that discrepancy was 7 sigma. In physics, 5 sigma is the threshold for calling something a discovery. It corresponds to a probability of roughly 1 in 3.5 million that the result is random noise. 7 sigma is not a louder version of 5 sigma. It is a qualitatively different situation. The probability that a 7 sigma deviation is a statistical fluctuation is smaller than 1 in a trillion. The CDF result was not a hint. It was a number that does not fit. and the team had been working on the measurement for a decade before publishing it. The Standard Model is a tightly coupled system. The W boson mass is not an isolated parameter. It is connected through precise mathematical relationships to the masses of the Higgs boson, the top quark, and the Z boson. If the real W boson mass differs from the prediction, something in those relationships is wrong. Not imprecise, structurally wrong. Other experiments have since measured the W boson mass and returned values closer to the Standard Model, which means the field now has a genuine conflict within its own data. Different measurements, different instruments, different results. That situation, where the data disagrees with itself at this level of precision, is something physics has not dealt with in this form before, and it has not been resolved. 3 years later, it is still open. The muon is not an exotic particle. It has been part of physics since 1936, when it appeared unexpectedly in cosmic ray experiments. Physicist Isidore Rabi, upon hearing the news, reportedly asked, "Who ordered that?" The muon was not predicted. It just showed up. And in the nearly 90 years since, physics has folded it into the Standard Model as essentially a heavier version of the electron. Same electric charge, same forces, different mass. The framework treats them as identical in every interaction except the ones that depend on mass directly. One of the quantities used to test that identity is the muon's anomalous magnetic moment, called G-2. It measures how strongly the muon responds to a magnetic field beyond the baseline prediction. The Standard Model calculates this number by accounting for every known particle that can briefly flicker into existence in the quantum vacuum and influence the muon's behavior. The calculation is extraordinarily precise, and it is supposed to match the measured value. For the electron, it does to 11 decimal places. For the muon, it does not. The Fermilab muon G2 experiment published results in 2021, 2022, and 2023. The combined deviation from the Standard Model sits at 4.2 sigma. Below 5, not a formal discovery. But 4.2 sigma across multiple independent runs, using different beam intensities and different analysis approaches, is not the kind of number that disappears with more data. It is a persistent signal. Either the Standard Model's calculation is missing a contribution from something that does not appear in the current theory, or the muon genuinely behaves differently than the electron in ways the framework does not account for. Neither of those options is a minor correction. Both of them require something new to be true. And when you line this up next to the W boson result, two separate measurements, two separate teams, two separate sectors of the theory, both pointing away from the prediction, the question stops being whether something is off and starts being what exactly is off. One of the load-bearing assumptions of the Standard Model is called Lepton universality. It states that the weak nuclear force couples identically to all three generations of leptons: electrons, muons, and tau particles, with differences only in proportion to their masses. In practice, this means that when a particle decays through the weak force into different types of leptons, the ratio of those decays follows a precise and predictable pattern. The electron and the muon should show up in the exact proportion the mathematics requires. Not approximately. Exactly. The LHCb experiment at CERN spent the better part of a decade measuring the decays of B mesons, particles built around a bottom quark, into final states that include either electrons or muons. Between 2013 and 2022, the data kept returning a ratio that deviated from the theoretical prediction. The muon final states were appearing less often than they should, with deviations reaching 3.3 sigma in certain angular distributions. The anomaly did not shrink as the dataset grew, it held. In 2022, LHCb released a reanalysis with a cleaner dataset that reduced the headline Lepton universality violation below 5 sigma. The field took a breath. But the angular anomaly, the P5 prime parameter in B to K star decays, remained at 3.3 sigma. The number did not move, and that number has been sitting in the data, unresolved, for over a decade now. So here is where we are after just these first measurements. The W boson mass does not match. The muon's magnetic behavior does not match. The B meson decay ratios do not match. 3 independent sectors of the standard model. 3 independent experimental teams. 3 deviations in the same operational window. The standard scientific response is to look for the error in each measurement separately. And physicists have been doing exactly that. They have not found the errors. What they have found instead is more data. And in that data, more of the same. The W boson mass does not match. The muon's magnetic moment does not match. The B meson decay ratios do not match. 3 separate experiments. 3 separate teams. 3 separate sectors of the theory. And all 3 deviations appeared in the same operational window, while the LHC was running at record energies with record precision. The standard response in physics when a measurement comes back wrong is to look for the error in the measurement. That is not cynicism. That is how science is supposed to work. Instruments have systematic biases. Analysis methods have blind spots. The history of particle physics is full of anomalies that dissolved when someone found the mistake. So when the W boson result came in at 7 sigma, the field went looking for the mistake. When the muon anomaly persisted across 3 years of independent runs, the field kept looking. When the B meson numbers held through a decade of updated analyses, the field looked harder. The errors have not been found. And here is what makes that significant. These are not 3 measurements of the same thing. The W boson and the muon have nothing directly to do with each other. The B meson decays involve a completely different force interaction. There is no obvious reason why a systematic error in one experiment would produce a correlated deviation in the others. For 3 independent measurements to each develop their own separate mistake, all pointing in the same direction at the same time, that requires a coincidence that becomes harder to believe with each passing year of additional data. There is a version of this story where all 3 anomalies get resolved individually. A better calculation here, a cleaner dataset there. But there is another version where they are not 3 separate problems, where they are the same underlying problem appearing in 3 different places, because the theory has a gap, and these measurements are all sitting near the edge of it. The data does not tell us which version is true. What it does tell us is that after 3 years and 50 quadrillion collisions, the deviations are still there. While the anomalies in the standard model were accumulating on one side of the ledger, something else was happening on the other side. The LHC was finding particles that the theory never predicted would exist, in the forms they were appearing in. In 2015, the LHCb experiment reported the first confirmed observation of a pentaquark, a particle made of 5 quarks bound together. In the decades before that result, the question of whether pentaquarks could exist had been genuinely contested. The rules of quantum chromodynamics, the theory that governs how quarks bind together, do not forbid 5 quark states, but they also do not naturally produce them. The expectation was that such configurations would be too unstable to observe cleanly. LHCb found them anyway, then found more in 2019, then more again in 2022, including an entire new family of pentaquark states with different quark compositions. Each discovery was confirmed independently. Each one represented a type of matter that the standard model technically allows, but never specifically predicted. And each one raised the same question in a slightly different form. If the theory permits these structures without predicting them, what else does it permit that nobody has thought to look for yet? The tetraquarks followed the same pattern, particles built from 4 quarks, including in 2021, the first particle ever found composed entirely of 4 heavy quarks. The theory had been checked for decades without anyone finding these states, not because they were forbidden, but because the theoretical tools for predicting exactly when and how they would appear were not precise enough. The LHC found them because it was running at energies and luminosities where the signals finally became visible above the noise. What the pentaquark and tetraquark results reveal, taken together, is that the interior structure of matter is richer than the standard model's predictions implied. Not richer in a way that breaks anything. Richer in a way that suggests the theory's picture of what is possible was drawn with less detail than the reality it was describing. In December 2025, CERN published the summary of the LHC's final full year of Run 3 operation. The numbers were, by any measure, extraordinary. The collider delivered 125 femtobarns of data to ATLAS and CMS over the course of the year, more than in any previous year of operation. The two experiments had now each accumulated 500 femtobarns of total collision data across the full run. The figure that kept appearing in the summary documents was 50 quadrillion. That is the approximate number of proton-proton collisions recorded across the lifetime of Run 3. 50 quadrillion individual moments where two particles moving at nearly the speed of light passed through each other, and the detectors captured what came out. The data volume matters for one specific reason. In particle physics, anomalies that are caused by statistical fluctuation get smaller as the dataset grows. More data means more precision, which means flukes get averaged out and real signals get stronger. That is the logic behind running the collider for years at a time. If something strange appears early, you run longer and watch what happens to it. What happened to the anomalies in Run 3 is that they did not get smaller. The W-boson discrepancy is unresolved. The muon G2 deviation has held across 4 years of dedicated measurements at Fermilab. The angular anomalies in B meson decays have been in the data for over a decade. 50 quadrillion collisions did not make them go away. In several cases, the additional data made the deviations more statistically robust, not less. That outcome is not what anyone was expecting when Run 3 began. The working assumption across much of the field was that the increased dataset would either confirm a clear signal of a new physics or wash out the existing hints into noise. Neither happened. The hints stayed exactly where they were, persistent, unresolved, and now supported by more data than any previous generation of experiments had access to. The machine ran longer and harder than ever before. The questions it was asked to settle are still open. When the Large Hadron Collider began its first run in 2010, there was a broad consensus in the theoretical physics community about what it would find. The Higgs boson was the headline target, the last missing piece of the standard model, predicted since 1964 and never observed. But alongside the Higgs, there was a second category of expected discoveries that most theorists considered nearly as certain. The LHC was going to find supersymmetric particles. Supersymmetry is a theoretical framework that proposes a symmetry between two fundamental classes of particles: the particles that make up matter and the particles that carry forces. For every known particle, supersymmetry predicts a partner particle with different quantum properties. The electron has a selectron, the quark has a squark, the photon has a photino. These partner particles were expected to be heavier than their standard model counterparts, which is why they had not been seen in lower energy experiments. The LHC, running at energies far beyond anything previously achieved, was supposed to be where they finally showed up. The theoretical case for supersymmetry was not based on wishful thinking. The framework solved several genuine problems in the standard model simultaneously. It offered a natural explanation for why the Higgs boson mass is stable against quantum corrections, a problem called the hierarchy problem that has no solution within the standard model itself. It provided a candidate particle for dark matter. It pointed toward a mathematical unification of the fundamental forces at high energies. Supersymmetry was not just an interesting idea. It was the leading candidate for the physics that had to exist beyond the standard model, supported by decades of theoretical work from hundreds of researchers. The LHC found the Higgs boson in 2012. It has not found a single supersymmetric particle, not a hint. not a marginal signal that required more data. After run 1, run 2, and now run 3, after 15 years of operation at successively higher energies, the supersymmetric particles that the theory said should be, there are simply not appearing. The mass ranges where they were expected have been searched and excluded. The searches keep going, pushing into higher mass territory, finding nothing. That outcome has consequences for how the field thinks about what comes next. Supersymmetry was not the only framework that predicted something the LHC has not found. For roughly 3 decades, the leading candidate for the identity of dark matter was a class of hypothetical particles called WIMPs, weakly interacting massive particles. The case for WIMPs rested on what physicists called the WIMP miracle. If you assumed a particle with roughly the mass of a heavy atomic nucleus that interacted through the weak force, the calculations naturally produced a relic abundance from the early universe that matched the observed dark matter density, almost exactly. The numbers worked out without being tuned to work out. That kind of coincidence in physics is usually a sign that something real is being pointed at. The LHC was supposed to be able to produce WIMPs directly in high-energy collisions. When 2 protons collide at sufficient energy, the collision products include not just visible particles, but potentially invisible ones. Particles that pass through the detector without depositing energy, leaving only an imbalance in the momentum of everything else. ATLAS and CMS have spent 15 years searching for exactly this signature. They have found nothing in the mass ranges where WIMPs were expected. The searches have been extended upward in mass, refined in methodology, repeated with larger datasets. The result has not changed. At the same time, dedicated underground dark matter detectors, instruments built specifically to catch the rare occasions when a dark matter particle might scatter off an atomic nucleus, have also come up empty in the mass ranges where WIMPs were predicted. The LUX experiment, the Xenon series, Panda-X, each one more sensitive than the last, each one finding no signal. Dark matter exists. That is not a hypothesis, it is the conclusion of decades of gravitational measurements. From galaxy rotation curves to gravitational lensing to the large-scale structure of the universe. Something with mass is out there, and it is not made of any particle in the standard model, but it is not WIMPs, at least not in the form and mass range that theory most naturally predicted. The most elegant solution to one of physics' biggest open problems has been ruled out. What is left is a set of alternative candidates, none of which carry the same theoretical weight that WIMPs did, and none of which have been confirmed. There is a number sitting at the center of particle physics that nobody knows how to explain. It is not a measurement that came back wrong. It is a calculation that comes back right. And the rightness of it is what creates the problem. The Higgs boson has a mass of approximately 125 gigaelectronvolts. That is the measured value, confirmed to high precision by both ATLAS and CMS. The issue is not the measurement. The issue is that when physicists calculate what the Higgs mass should be, accounting for all the quantum corrections that come from every other particle in the theory, the result is not 125 gigaelectronvolts. The result is something closer to 10 million billion gigaelectronvolts, roughly the Planck scale, the energy at which quantum gravity becomes relevant. The standard model, left to its own devices, predicts a Higgs mass that is 10 to the 17th power larger than what is actually observed. To get the calculated value down to the measured value, the positive and negative contributions from quantum corrections have to cancel each other out with a precision of 1 part in 10 to the 34th. That is a number that has no physical intuition behind it. It is the equivalent of 2 quantities, each of which is incomprehensibly large, cancelling each other to leave a remainder that is incomprehensibly small, not because there is a mechanism forcing that cancellation, but apparently by coincidence. Supersymmetry was the most natural solution to this problem. The partner particles it predicted would provide the cancellation mechanism automatically, through a symmetry that made the result stable, rather than accidental. Without supersymmetry, there is no known mechanism that explains why the Higgs mass is what it is. The standard model requires a coincidence at the 34th decimal place, and offers no explanation for why that coincidence should occur. This is the hierarchy problem. It was not solved by finding the Higgs in 2012. It was made sharper. In 2022, after combining the full Run 2 dataset, ATLAS and CMS published the most precise measurement of the Higgs boson mass ever recorded, 125.25 giga-electron-volts. The uncertainty was smaller than 0.5%. It was by every technical measure exactly the kind of result the field had been working toward for a decade. It was also quietly the worst possible number. Here is the thing about the Higgs field that does not come up often enough. The Higgs is not just a particle, it is a field that fills all of space, and like any field in quantum physics, it sits in an energy state. That energy state has a shape. Think of it like a landscape. The field settles into a valley, a low point. The question is whether that valley is the lowest point in the landscape, or whether there is a deeper valley somewhere further down that the field has not yet reached. If the Higgs field is sitting in the true lowest point, the universe is stable. It stays exactly as it is. If the field is sitting in a false low point, a valley that looks like the bottom but is not, then the universe is in what physicists call a metastable state. It holds together not because it is at the bottom, but because the barrier between where it is and where it could go is high enough that getting over it is extraordinarily unlikely. When physicists feed the measured Higgs mass of 125.25 giga-electron-volts into the stability calculations, the answer that comes back is metastable, not stable, not already unstable, which would have resolved itself long before now, right in the middle. The number sits in a range where the current state of the universe is technically not the ground state. There is a lower state. The laws of physics allow a transition to it. The probability of that transition happening on any timescale that means anything is so small that it is not a practical concern. I think what is worth sitting with here is not the implication, but the fact itself. The most precise measurement ever made of the particle responsible for the mass of all matter in the universe placed the entire physical structure of observable reality in a configuration that is not, technically, the lowest energy state available to it. That is a strange thing to know. And it is a strange thing to have learned from a measurement that was considered a success. The 2022 result did not create a problem. It revealed the shape of one that was already there. The Higgs mass had to land somewhere. It landed in the one range where the answer to the stability question is neither yes nor no, where the universe is, in the precise technical language of quantum field theory, sitting in a local minimum rather than a global one. Whether that means anything beyond the mathematics is a question the field does not have a consensus answer to. What it does mean is that the most precisely measured number in the 2022 dataset pointed, without anyone planning it, directly at one of the deepest open questions in theoretical physics. Here is a number worth sitting with. The standard model, the theoretical framework that describes every particle and every force that has ever been directly detected, accounts for approximately 5% of the total energy content of the universe. The other 95% is divided between dark matter, which makes up roughly 27%, and dark energy, which accounts for the remaining 68%. Neither dark matter nor dark energy appears anywhere in the standard model. There are no particles in the theory that correspond to them. There is no force carrier, no field, no mechanism. They are not described. They are not even approximately described. This is not a gap at the edges of the theory. It is a gap at the center of it. The standard model is not a nearly complete description of reality with a few pieces missing. It is a precise and extraordinarily well-tested description of a small fraction of what exists, surrounded on all sides by phenomena it cannot address. Every time a telescope measures the rotation curve of a galaxy and finds that the visible matter cannot account for the gravitational behavior. That is the standard model's boundary becoming visible. Every time a cosmological survey maps the large-scale structure of the universe and finds filaments and voids that only make sense if there is a dark matter scaffold underlying them, that is the same boundary. The LHC was the best tool ever built for finding what lies beyond that boundary. It was designed and operated with the explicit goal of discovering the particles that make up the missing 95%. After 15 years of operation, it has not found them. Not a signal. Not a hint that survived closer scrutiny. The boundary is still there, exactly where it was before the collider turned on, now just more precisely mapped. There is a question about the early universe that the standard model cannot answer, and the consequences of that failure are about as personal as physics gets. The question is why matter exists at all. In the first moments after the Big Bang, the conditions of the universe produced matter and antimatter in equal quantities. Every particle of matter had a corresponding particle of antimatter. When the two meet, they convert entirely into energy. They cancel each other out completely, leaving nothing behind except radiation. If the early universe produced them in equal amounts, that is exactly what should have happened. Total cancellation. A universe filled with light and absolutely nothing made of matter. The universe contains matter. Everything in it, every star, every planet, every atom of every element exists because somewhere in the first seconds, a slight imbalance existed between matter and antimatter. Roughly one extra matter particle for every billion matter-antimatter pairs. Everything that exists today came from that excess. The billion pairs cancelled out. The one leftover particle survived. Multiply that by the total number of particles produced in the Big Bang, and you get a universe. The standard model predicts a mechanism for generating this imbalance, called CP violation, a subtle difference in how matter and antimatter behave under certain conditions. The LHCb experiment has spent years measuring CP violation in various particle systems and has found it. The first direct observation of CP violation in charm quarks came in 2019. The mechanism is real, but when physicists calculate how much imbalance the standard model's CP violation can actually generate, the answer is roughly a billion times too small. The mechanism exists, it just does not work at the scale required to explain why the observable universe is full of matter, rather than nothing. Something else generated that imbalance. That something is not in the current theory, and without it, the standard model cannot explain the most basic fact about the universe, that there is anything in it at all. I think that is worth stopping on for a moment. Not the technical details, just the fact itself. The best theory of matter that science has ever produced cannot explain why matter exists. That is not a minor gap. The first direct evidence that the standard model was incomplete did not come from the LHC. It came from a detector buried under a mountain in Japan in 1998, and it involved the least dramatic particle in the entire theory. Neutrinos are produced in enormous quantities by nuclear reactions. In the sun, in the atmosphere, in nuclear reactors. They interact so weakly with ordinary matter that they pass through the entire Earth almost without noticing it. The original standard model predicted that neutrinos, unlike most other particles, have exactly zero mass, not small mass, zero. The theory was constructed that way, and the prediction seemed consistent with everything measured for decades. In 1998, the Super Kamiokande experiment in Japan published evidence that neutrinos oscillate. That a neutrino produced as one type can transform into another type as it travels. This is only possible if the different types have different masses, which is only possible if at least some of them have non-zero mass. The standard model, as written, predicts that this cannot happen. The data showed that it does. Neutrino oscillation has since been confirmed by dozens of independent experiments. It is one of the most robustly established results in particle physics. It is also a direct proof that the standard model is incomplete, Not incomplete at the edge of its range, not incomplete at energies it was never designed to address, but incomplete in its description of the most abundant type of matter, particle in the universe. The theory was wrong about something fundamental, and it was wrong decades before the LHC was built. What the collider has been doing ever since is mapping how far that incompleteness extends. There is an anomaly built directly into the structure of the Standard Model that has been known since the 1970s and has never been resolved. It does not make headlines the way the LHC results do. It does not involve a dramatic experimental deviation or an unexpected observation. It is a theoretical problem, a place where the equations of the Standard Model allow something that experiments show does not happen, and nobody knows why. The strong nuclear force, the interaction that holds quarks together inside protons and neutrons, is described by a theory called quantum chromodynamics. The equations of that theory contain a parameter called theta that controls how much the strong force violates a symmetry between matter and antimatter. The equations allow theta to take any value between 0 and 2 pi. Experimental measurements of the neutron's electric dipole moment constrain theta to be smaller than 10 to the negative 10. Essentially, 0. There is no known reason within the Standard Model why theta should be so close to 0. The theory places no special significance on 0. Theta could have been anything, and from the perspective of the mathematics, any value would be equally natural. The fact that it is measured to be essentially 0 requires an explanation that the Standard Model does not provide. This is called the strong CP problem. One proposed solution involves a new particle called the Axion, predicted in 1977 by Roberto Pettei and Helen Quinn. The Axion would dynamically drive theta towards 0 through a symmetry-breaking mechanism. It has never been observed. Dedicated Axion searches, including several currently operating experiments, have constrained the available parameter space significantly, but have found no signal. As of 2026, the strong CP problem remains open, the Axion remains undetected, and the Standard Model continues to require, without explanation, that a free parameter take a value indistinguishable from 0. The tension in the LHC data is not the only place where physics is producing numbers that do not agree with each other. There is a second conflict, running in parallel, that involves the largest scales in cosmology rather than the smaller scales in particle physics. And the two measurement methods involved are so independent of each other that resolving the conflict by finding an error in one of them has become increasingly difficult to argue. The Hubble constant describes the rate at which the universe is currently expanding. It can be measured in two fundamentally different ways. The first uses observations of the early universe, specifically the cosmic microwave background, the afterglow radiation from roughly 380,000 years after the Big Bang, to extrapolate forward to the present expansion rate. The Planck satellite has measured this value with extraordinary precision. The second method uses distance ladder measurements in the local universe, observations of Cepheid variable stars, and Type 1a supernovae to directly measure how fast nearby galaxies are receding. The SH0ES collaboration has refined this measurement across decades of observations. The two methods give different answers. The early universe method gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The local measurement gives approximately 73. The discrepancy between these two numbers has reached 4.5 sigma. At that level of statistical significance, the probability that the disagreement is a coincidence is smaller than 1 in 100,000. Both measurements have been checked extensively by independent teams using different instruments and different methods. The discrepancy has not resolved as the datasets have grown. It has become more statistically significant. The Hubble tension, as it is called, suggests that either one of the measurement methods has an unidentified systematic error, or the cosmological model that connects the early universe to the present is missing something. A missing component in the model would mean new physics. something in the evolution of the universe between the early epoch and today that the standard cosmological framework does not account for. That something does not appear in the standard model of particle physics either. In parallel with the search for new particles, one of the LHC experiments has spent its entire operational lifetime studying something that is not a particle at all. The ALICE detector was built specifically to investigate heavy ion collisions, not proton-proton collisions, but collisions between entire lead nuclei, each containing over 200 protons and neutrons. When two lead nuclei collide at LHC energies, the energy density in the collision region briefly exceeds the threshold at which protons and neutrons dissolve. The quarks and gluons that make them up are released into a state of matter called quark-gluon plasma. Quark-gluon plasma is the state that filled the universe in the first microseconds after the Big Bang, before the universe cooled enough for quarks to bind into protons and neutrons. It has not existed naturally anywhere in the observable universe since that period. ALICE recreates it in a volume smaller than an atomic nucleus, for a duration measured in yoctoseconds, and studies its properties before it cools and hadronizes back into ordinary particles. The results have been consistently surprising. Theoretical predictions, based on the equations of quantum chromodynamics, described quark-gluon plasma as a weakly interacting gas. A system where the quarks and gluons would move relatively freely because the strong force becomes weaker at high energies. What ALICE found was the opposite. Quark-gluon plasma behaves like a nearly perfect liquid, with a viscosity so close to zero that it represents the lowest viscosity to entropy ratio of any substance ever measured. The theoretical picture of a gas was wrong. The actual substance is the most perfect fluid known to physics. Understanding why the equations predicted one thing and the experiment found another remains an active area of research. In 2025, for the first time in the collider's history, the LHC ran collisions involving oxygen nuclei, proton-oxygen collisions, oxygen-oxygen collisions. This was not a routine extension of the heavy ion program. It was a targeted experiment designed to answer a specific question about where quark-gluon plasma formation begins. The conventional picture, established through years of lead-lead collision data, was that producing quark-gluon plasma required the enormous energy densities achievable only in collisions between large, heavy nuclei. Lead, with its 208 nucleons, was the standard choice. Smaller nuclei were expected to produce less extreme conditions, enough to study the nuclear structure, but not enough to dissolve the nucleons into their constituent quarks and gluons. The 2025 oxygen results changed that picture. Early results from ALICE showed significant evidence of quark-gluon plasma formation in oxygen-oxygen collisions. A nucleus with only 16 nucleons, more than 12 times smaller than lead. The threshold for producing this state of matter turned out to be considerably lower than the field had assumed. The conditions that existed in the first microseconds of the universe are apparently more accessible than anyone expected. That result has implications beyond heavy ion physics. If quark-gluon plasma can form in nuclei as small as oxygen, the question of where the boundary lies, and what the physics near that boundary looks like, opens up a new range of experimental territory. The same 2025 run also confirmed, for the first time directly, that the neon nucleus has an elongated shape rather than the spherical shape that nuclear models had assigned to it for decades. Two separate results from the same run, both requiring revisions to accepted pictures of nuclear structure and behavior. In 2025, the ATLAS collaboration published the results of a search unlike any previous analysis in the experiment's history. Previous searches for new physics at the LHC had all shared a common structure. A theoretical prediction specified what new particles might exist and what their experimental signatures would look like, and the analysis was designed to look for those specific signatures in the data. The search was always guided by theory. The question was always, Does the data contain evidence of this particular predicted thing? The 2025 analysis inverted that structure. Using an unsupervised machine learning algorithm, Atlas searched for anomalous collision events without specifying in advance what the anomaly should look like. The algorithm was trained on standard model collision events, learned what normal collisions look like, and then flagged events that deviated significantly from that learned picture, without any theoretical input about what the deviation should be. The motivation for this approach is straightforward. If the new physics that lies beyond the standard model produces signatures that no current theory predicts, a theory-guided search will never find it. The data could contain evidence of something genuinely unexpected, and every conventional analysis would pass over it because nobody told the analysis to look there. The unsupervised search is an acknowledgement that the theoretical imagination of the field may have limits that the data does not share. The 2025 results did not report a discovery. The anomalous events flagged by the algorithm were consistent with rare standard model processes after detailed follow-up analysis. But the method itself represents a shift in how the field approaches the problem of finding new physics. After 15 years of theory-guided searches returning empty results, the experiment is now asking the data what it contains, rather than asking whether it contains what theory predicted. By the end of Run 3, the landscape of particle physics searches looked like this. Every supersymmetric particle in the mass ranges where it was expected has been excluded. The WIMP dark matter candidates most favored by theory have been ruled out across their preferred mass ranges. Additional Higgs bosons, predicted by several extensions of the standard model, have not appeared. Extra dimensions of space, predicted by models that would solve the hierarchy problem, have produced no detectable signature in the graviton searches. Magnetic monopoles, which would complete the symmetry between electricity and magnetism, and are predicted by several grand unified theories, have not been found. Each of these searches returned a null result. In the conventional framing, a null result is a failure. The experiment looked for something and did not find it. But there is another way to read the accumulated null results of Run 3. They are not just failures to find specific particles, they are constraints on what can be true. Each exclusion narrows the space of viable theories. Together, they have eliminated a large fraction of the theoretical landscape that physicists considered most promising in the years before the LHC turned on. What is left after that elimination is a theoretical situation that the field was not prepared for. The anomalies that exist, the W boson mass, the muon G2, the B meson deviations, require new physics to explain. But the searches for the specific types of new physics that theorists expected have all come up empty. The data is pointing towards something, and simultaneously ruling out the most natural candidates for what that something is. That combination, positive hints in precision measurements, negative results in direct searches, is the defining feature of the Run 3 legacy. And it is a harder problem to address than either category of result would be on its own. In December 2025, the European Strategy Group for Particle Physics met in Ascona, Switzerland, and issued a set of recommendations that will shape the direction of the field for the next several decades. The primary recommendation was to build the Future Circular Collider, a new electron-positron collider with a circumference of approximately 91 kilometers, to be constructed in the Geneva Basin on a timeline that would see first collisions in the early 2040s. The choice of an electron-positron collider rather than a proton-proton collider is significant. Proton colliders like the LHC are discovery machines. They reach the highest energies and search broad territory, but the collisions are messy, involving composite particles whose interactions are difficult to calculate precisely. Electron-positron colliders are precision machines. The collisions involve fundamental particles with well-defined energies, producing clean data that allows measurements of extraordinary precision. The FCC-ee is designed primarily to study the Higgs boson, the W boson, the Z boson, and the top quark with precisions that the LHC cannot approach. The strategic logic behind this choice is a direct response to the Run-3 situation. The anomalies that have accumulated, the W boson mass, the muon G2, the Higgs coupling measurements, are all in the regime of precision measurements, rather than direct discovery. They suggest that whatever lies beyond the standard model may not manifest as new heavy particles at accessible energies, but instead as small deviations in the properties of known particles. If that is correct, the path forward is not a higher energy discovery machine, it is a higher precision measurement machine. The FCC-ee is the answer to that specific problem. The decision to recommend it, with a final vote expected in Budapest in May 2026, represents the field's collective judgment about what the Run-3 data is telling them to do next. In the middle of 2026, the Large Hadron Collider will stop running for the last time in its current form. The shutdown is planned and scheduled. It is the beginning of a multi-year upgrade program called Long Shutdown 3, during which the collider and its detectors will be rebuilt into the high luminosity LHC, a significantly more capable machine designed to deliver 10 times the data rate of the current accelerator. The shutdown is not a failure. It is the natural endpoint of a planned operational cycle, and the upgrade that follows it represents a substantial investment in the future of the experimental program. The high luminosity LHC is scheduled to begin operations around 2030 and run through approximately 2041, and the physics program it enables, with datasets far larger than anything Run-3 produced, will allow tests of the standard model at precisions currently out of reach. But the shutdown also marks the close of a specific chapter. Run-3 is the last data-taking period of the LHC as it currently exists. The 50 quadrillion collisions it recorded are the complete dataset from this machine at these energies. Whatever answers those data contain are, in principle, accessible now, waiting in the analysis pipeline for someone to pull them out, as Toponium waited until the 2025 analysis found it. And whatever questions the Run-3 data raises but cannot answer will wait for the next machine to address them. The list of open questions that passes from Run-3 to the high luminosity LHC is long. The W boson mass conflict is unresolved. The muon anomaly is unresolved. The matter-antimatter asymmetry is unexplained. Dark matter has no identified particle. The hierarchy problem has no solution. The strong CP problem has no mechanism. The Hubble tension has no agreed explanation. The machine that just finished its run did not solve these problems. It documented them with unprecedented precision, eliminated the most favored theoretical solutions, and handed the problems to the next generation of instruments in sharper form than they were received. There is something uncomfortable about the standard model's track record that becomes visible only when you look at it from a specific angle. Every successful prediction the theory has ever made was a prediction about something it was built to describe. The W boson mass, it was built to predict that. The Higgs boson, built to predict that. The behavior of quarks inside protons, built to predict that. 50 years of experimental confirmation is real and it is extraordinary. But 50 years of being right within a defined territory does not mean the territory covers everything. Here is what the theory was never built to explain. It was never built to explain dark matter. There is no dark matter particle in its equations. It was never built to explain dark energy. The cosmological constant is general relativity's problem, not the standard models. It was never built to explain why the Higgs mass is stable against quantum corrections, or why there are exactly 3 generations of matter particles, or why the coupling constants have the values they do rather than some other values. These are not questions at the edges of the theory. They are questions the theory explicitly does not address. I think the 50-year record gets misread sometimes. It gets read as evidence that the theory is nearly complete, that it describes almost everything and just needs a few final pieces. The actual record is different. It is a theory that is precise and complete within a specific domain, surrounded on all sides by phenomena it was never designed to touch. Run 3 did not reveal that the theory was failing. It revealed, more clearly than any previous experiment, exactly where the domain ends. That boundary has always been there. The LHC just mapped it with better instruments than anyone had before. The standard story about scientific progress goes like this. An anomaly appears. It resists explanation. It grows into a crisis. A new theory resolves it. Everyone moves on. The current situation does not fit that story cleanly. The anomalies are there. The W boson mass, the muon G2, the B meson deviations. The resistance to explanation is there. 3 years of additional data have not resolved any of them. What is missing is the third part. There is no leading theoretical candidate that explains all 3 anomalies simultaneously, makes new predictions, and has broad support across the field. There are proposals, there are frameworks. None of them carry the kind of theoretical weight that supersymmetry carried in 1994 when the LHC was approved. What the field is actually sitting with right now is something more uncomfortable than a crisis with a known resolution. It is a situation where the experiments are telling everyone that something beyond the current theory exists. The anomalies are too persistent to be noise, but the theoretical imagination of the field has not yet produced the framework that would make sense of them. The anomalies are real. The answer is not yet visible. This has happened before in physics. The null result of the Michelson-Morley experiment in 1887 demonstrated that the ether did not exist. But special relativity, which explained why, did not come until 1905. 18 years of knowing the old picture was wrong before the new picture arrived. The current gap between experimental signal and theoretical resolution may be shorter than that. It may be longer. I think the honest answer is that nobody knows, and the people who say they do are guessing. While the direct searches at the LHC were coming up empty, a completely different experimental strategy was producing the results that have proven most durable. Instead of trying to produce new particles directly in collisions, precision measurements look for the indirect effects of those particles on quantities that can be calculated and measured with extreme accuracy. The logic works like this. If a new particle exists above the energy reach of current colliders, it cannot be produced and detected directly. But it can still appear virtually, flickering in and out of existence in quantum processes that influence the behavior of known particles. Those influences are small, but if the measurement is precise enough, they become detectable as tiny deviations from the standard model prediction. The muon G2 is the clearest current example. No new particle was directly produced, no new signature appeared in a detector. What appeared instead was a number, the muon's magnetic moment, that sits 4.2 sigma away from the theoretical calculation after 4 years of independent measurements. If that deviation is eventually confirmed as real physics rather than a calculational error, it will have been found through precision, not through energy. The charm quark was found this way before it was directly produced. The top quark mass was constrained this way before the tevatron found the particle itself. The FCC-ee, if it gets built, is essentially a precision machine at a scale that makes the current generation look approximate. It would measure Higgs couplings, W boson properties, and top quark behavior with precisions an order of magnitude beyond what the LHC can achieve. The strategic logic behind recommending it, rather than a higher energy proton collider, is a direct response to what Run 3 taught the field. The new physics may not be sitting at higher energies waiting to be produced. It may be sitting in the precise values of known quantities, waiting for an instrument sensitive enough to see it. Among all the theoretical proposals that survived the Run 3 exclusions, one of the most interesting is also one of the oldest, and it was not invented to solve the problem most people associate it with today. In 1977, Roberto Pache and Helen Quinn proposed a new symmetry in the equations of quantum chromodynamics. Their motivation was the strong CP problem, the unexplained fact that the strong force does not violate matter-antimatter symmetry, even though the equations allow it to. The symmetry they proposed would dynamically drive the relevant parameter towards zero, fixing the problem. As a byproduct of that symmetry breaking, the theory predicted a new particle. Frank Wilczek, who later won the Nobel Prize for other work in QCD, named it the Axion after a laundry detergent. The name stuck. For roughly 2 decades, the Axion was a solution to a technical problem that most physicists considered somewhat obscure. Then cosmologists noticed something. The properties that make the Axion solve the strong CP problem, very light, very weakly interacting, also make it a viable dark matter candidate. A particle that fixes one open problem and provides an answer to another simultaneously is theoretically attractive in a way that goes beyond aesthetics. It is the kind of coincidence that physics takes seriously. Axion searches have multiplied. ADMX in the United States, Haystack at Yale, CAPP in South Korea. Several experiments at CERN. As of 2026, none have found a confirmed signal. But the searches are covering new territory with each generation, and the parameter space for axions is large enough that the absence of a detection so far does not rule them out. In the landscape that Run 3 left behind, where the most favoured candidates have been excluded and the theoretical options have narrowed, a particle that could solve 2 problems at once gets more attention, not less. There is an issue sitting at the center of the standard model that does not generate dramatic experimental results and does not make headlines, but that underlies the current theoretical situation in a way that is worth being direct about. The standard model contains roughly 19 free parameters. These are quantities, being particle masses, coupling strengths, mixing angles, whose values the theory does not predict. They have to be measured in experiments and inserted into the equations by hand. The theory then works correctly with whatever values are put in, but it offers no explanation for why those values are what they are rather than something else entirely. This is not a minor issue. The hierarchy problem is a problem about why one of those parameters, the Higgs mass, is so much smaller than it should be given the quantum corrections that act on it. The strong CP problem is a problem about why another parameter, theta in QCD, is so close to zero when nothing in the theory requires it to be. The matter-antimatter asymmetry question is partly a question about where the CP violating parameter got its value. 3 of the biggest open problems in particle physics are, at their core, the same kind of problem. Why do the free parameters of the standard model have the values they do? And what determines those values? Supersymmetry provided mechanisms that addressed some of these parameter problems naturally, particularly the hierarchy problem. Extra dimensions provided others. Those frameworks have been excluded by the LHC data. What remains is a theory with 19 numbers that have to be put in by hand, no mechanism explaining any of them, and a set of experimental hints suggesting that something beyond the theory exists. The hints are real. The mechanism that would explain them is not yet known. That is the actual state of particle physics in 2026, stated plainly. Step back from the individual results. The specific anomalies, the specific exclusions, the specific measurements, and look at what Run 3 produced as a complete document. There is a pattern in it that becomes clearer when the pieces are held together rather than examined one at a time. Within the domain it was designed to describe, the standard model performed exactly as expected. Measurements of production rates, decay probabilities, and coupling strengths matched theoretical calculations with precisions that in several cases exceeded anything previously achieved. The theory was not failing where it had always succeeded. Every test within its designed range came back confirming the framework. At the boundary of that range, the picture looks different. The W boson is slightly heavier than predicted. The muon responds slightly more strongly to magnetic fields than predicted. The B meson decay ratios are slightly off. The Higgs mass sits at a value that raises questions about vacuum stability. None of these deviations, alone, forces a revision of anything. Together, they describe a theory performing exactly as a theory performs when it is approaching the edge of where it applies, accurate at the center, increasingly strained at the margins. I think the honest read of the Run 3 dataset is this. It is not evidence that the standard model is wrong. It is evidence that the standard model is bounded, that it describes a specific domain precisely, and that the physics outside that domain is real, measurable through its indirect effects, and not yet understood. The machine spent 3 years mapping that boundary with the best instruments ever built for the purpose. The map is more detailed than it has ever been. What it shows is not a complete picture. It shows exactly how far the current understanding reaches and exactly where it stops. The high luminosity LHC is not a new collider. It is an upgrade, new superconducting magnets, rebuilt detectors, new data acquisition systems, designed to deliver roughly 10 times the collision rate of the current machine. The upgrade program is called Long Shutdown 3. It begins in 2026, and the upgraded machine is scheduled to begin operation around 2030. By the time it finishes in the early 2040s, it will have delivered a total dataset roughly 6 times larger than everything Run 1, Run 2, and Run 3 produced combined. That scale matters for specific reasons. The anomalies that persist in the current data, the W boson mass, the muon G2, the B meson angular distributions, are all in a regime where more data directly translates to higher statistical significance. If they are real physics, the high luminosity LHC will either push them to the level of a formal discovery or reveal them as systematic effects that disappear with better statistics. There is no third option at that dataset size. The question gets answered. The direct searches will also continue, pushing into higher mass territories that Run 3 could not fully cover. Supersymmetric particles at higher masses, dark matter candidates in unexplored parameter space, additional Higgs bosons with different coupling patterns, all of these remain targets. The exclusions from Run 3 are real, but they do not cover the full range of possibilities. The upgraded machine extends the reach. What the high luminosity LHC cannot do is what the FCC-ee is designed for: measure the Higgs self-coupling precisely enough to determine the actual shape of the Higgs potential, or test the electroweak sector at precisions that would reveal small deviations caused by new particles far above direct production energy. Those measurements require a different type of machine. The strategic logic of the field in 2026 is that both types are needed, and the sequencing between them will be decided in Budapest. There is a phrase that started appearing with increasing frequency in physics papers and conference talks after the LHC's first runs returned no supersymmetric particles. The phrase is Post-naturalness era. It refers to the period after the expectation of finding a natural solution to the hierarchy problem at TeV energies was ruled out by the data. Naturalness was not just an aesthetic preference among theorists. It was a principle that shaped 3 decades of theoretical work, influenced career choices, guided the design of experiments, and generated a specific and detailed set of predictions about what the LHC would find. The expectation that supersymmetric particles would appear at TeV scale energies was so widespread in the field that it was treated, in many corners, as a near certainty. When those particles did not appear after Run 1, the field waited for Run 2. After Run 2, it waited for Run 3. After Run 3, the waiting is over and the particles are not there. What the post-naturalness era looks like in practice is a theoretical landscape with no consensus candidate. There are proposals, extended Higgs sectors, composite Higgs models, dark photon frameworks, various approaches to the hierarchy problem that accept fine-tuning and try to understand it through other means. None of these have the theoretical support that supersymmetry had. None make predictions as specific and testable as supersymmetry's predictions turned out to be. The theoretical community is genuinely uncertain about which direction to develop, in a way that has not been true since before the standard model was assembled. I think this is actually the most significant legacy of Run 3 that does not get talked about enough. Not the anomalies. Those are measurable and will eventually resolve. The deeper legacy is that the LHC eliminated the theoretical framework that was guiding the field's intuitions about what comes next. The experimental data is ahead of the theory right now. That is an uncomfortable position. It is also, historically, where the most interesting physics tends to come from. In 1900, the physicist Lord Kelvin gave a lecture in which he described the physics of the time as nearly complete. 2 small clouds remained on the horizon, he said. The first was the failure of the Michelson-Morley experiment to detect the ether. The second was the inability of classical physics to explain blackbody radiation. Both seemed like minor technical problems that would be resolved with minor adjustments to existing frameworks. The resolution of those 2 clouds produced special relativity and quantum mechanics. The 2 most consequential theoretical developments in the history of physics came directly from treating those small anomalies as real problems rather than nuisances waiting for a clean explanation. The parallel to the current situation is not perfect. It never is. But the structural similarity is worth noting. The standard model is not in the position classical physics was in 1900. It is not nearly complete, and it does not describe nearly everything. It is precise within its domain and explicitly incomplete outside it. The anomalies of Run 3 are not small clouds on the horizon of an otherwise settled picture. They are signals from a boundary that the theory was always known to have. What comes after the boundary? What theoretical framework eventually makes sense of the dark matter, the matter-antimatter asymmetry, the hierarchy problem, the persistent deviations in precision measurements, is genuinely unknown. I do not think anyone in the field would tell you otherwise with a straight face. What history suggests is that when the anomalies are real and the experimental data is precise enough, the resolution eventually arrives. It tends to arrive in a form that nobody predicted exactly. And it tends to make the previous theoretical landscape look, in retrospect, like an approximation to something richer. Here is a way to think about where physics stands in 2026 that does not require understanding any of the specific experimental results. The standard model is a theory of matter and forces. It describes particles and their interactions. It has been tested across an enormous range of energies and phenomena. Within its domain, it works. That domain covers approximately 5% of the total energy content of the universe. The 5% that consists of ordinary matter, atoms, molecules, everything made of protons, neutrons, and electrons. The remaining 95% is divided between dark matter and dark energy. Dark matter makes up roughly 27%. Dark energy accounts for the remaining 68%. Neither appears anywhere in the standard model. There are no particles in the theory that correspond to them. There is no force, no field, no mechanism. They are not described. They are not approximately described. They are simply outside the scope of the theory entirely. This is not a gap at the edges of an otherwise complete picture. It is a gap that covers most of what exists. The standard model describes the minority fraction of reality with extraordinary precision, and has nothing to say about the majority. Run 3 mapped the boundary of that minority fraction with the best instruments ever built for the purpose. Every null result in the direct searches, the absent supersymmetric particles, the missing dark matter candidates, was the experiment confirming that the boundary is real and that what lies beyond it does not look like what the theories predicted. That is what 50 quadrillion collisions and 15 years of operation produced. Not a failure, a map. The most detailed map ever made of the edge of what physics currently understands. What is on the other side of the edge is the next question. When the LHC stops running in 2026 for its upgrade, the legacy it leaves is genuinely hard to characterize in a single sentence. Both things are true at the same time, and holding them together is important. On one side, the Higgs boson was found. Dozens of new hadron states were discovered. Quark-gluon plasma was studied in detail that was not previously possible. The standard model was tested at energies and precisions far beyond anything the previous generation of experiments could access, and it held. The top quarks properties were measured to levels that would have seemed unreachable when the LHC was approved. Toponium was observed. The shape of neon nuclei was measured directly for the first time. These are real achievements. On the other side, supersymmetry was not found. Dark matter has no identified particle. The hierarchy problem has no solution. The matter-antimatter asymmetry has no mechanism. The W-boson mass conflict is unresolved. The muon anomaly is unresolved. The machine finished its run with those problems in the same state it found them, except more precisely characterized, and with more of the obvious solutions ruled out. Both of these things are true simultaneously. I think the instinct to resolve them into a single verdict, triumph or failure, is the wrong instinct. The LHC was built to extend the boundary of what could be measured and tested. It did that. What it found at that boundary was not a neat resolution of the existing open questions. It was a sharper picture of how deep those questions actually go. That is what the best scientific instruments do. They do not close questions. They show you exactly where your current understanding reaches, and exactly where it stops. The Large Hadron Collider was approved in 1994. It took 15 years to build. The original construction cost was approximately 5 billion Swiss francs. Over 10,000 scientists from more than 100 countries have contributed to its experiments. By any measure, it is one of the most complex scientific instruments ever constructed, and the collaboration required to build and operate it represents something close to the full extent of what organized human effort can produce in a single scientific project. That investment was made against a specific set of expectations. The Higgs boson would be found. It was. Supersymmetric particles would likely appear at TeV scale energies. They did not. Whatever resolved the hierarchy problem would become visible. Nothing did. The machine delivered everything it was capable of delivering. The universe did not deliver what the theories of 1994 predicted would be there to find. That gap between expectation and result is information. It tells the field that the theoretical intuitions guiding the experimental program were partially wrong. Not about whether new physics exists, but about what form it takes, and at what energy scales it becomes directly accessible. 15 years of operation at the energy frontier produced an extensive map of what is not at that frontier. That is a genuine scientific result, even if it is not the one anyone was hoping for. The collider has been measuring the shape of the unknown. The shape it found is different from the shape that was expected. Understanding why, and what the actual shape implies about the physics that lies beyond it, is the work that passes from this generation of instruments to the next. Physics operates on scales that have no natural human equivalent. The particles the LHC studies are smaller than anything visible under any microscope. The energies involved are concentrated into regions smaller than a proton. The timescales on which events occur require scientific notation just to write down. The distances range from the radius of a quark to the size of the observable universe, a span of roughly 42 orders of magnitude. Working at these scales requires building conceptual frameworks that function correctly, even when they produce results that feel completely wrong. Quantum mechanics says a particle can be in two places at once until it is measured. Special relativity says moving clocks run slower than stationary ones. These are not intuitive statements. They are statements that contradict the picture of the world that human cognition evolved to navigate. The standard model is built on top of both of them, and its predictions are frequently stranger than either. What makes the current moment in physics interesting is the specific combination of conditions it presents. The experimental instruments are more capable than they have ever been. The datasets are larger than they have ever been. The measurement techniques are more refined than they have ever been. And the theoretical picture of what those measurements are pointing toward is less settled than it has been at any point in the past 50 years. The experiments are doing their job. The data is coming in clean. The anomalies are persistent and increasingly well characterized. What is not keeping pace is the theoretical side, the framework that would make sense of what the data is showing. The instruments are ahead of the ideas right now. That is an unusual situation, and in the history of the field, it has tended to precede something significant. There is a tendency, when discussing the limits of scientific knowledge, to frame the open questions as failures. Things that should have been solved, problems that represent gaps in understanding that need to be fixed as quickly as possible. That framing is understandable. It is also incomplete. The open questions in particle physics in 2026, dark matter, the matter-antimatter asymmetry, the hierarchy problem, the strong CP problem, the Hubble tension, are not deficiencies in the sense of things going wrong. They are the places where the known and the unknown are in direct contact. They are the locations where the current theory meets the phenomena it cannot explain. They are, in the most direct sense, where the interesting work is. I think the history of what fundamental physics has produced, not just as knowledge but as technology, is worth keeping in mind here. Quantum mechanics was developed to explain anomalies in blackbody radiation and the photoelectric effect. The practical result was semiconductor technology, lasers, and medical imaging. General relativity was developed to address incompleteness in Newtonian gravity. The practical result includes GPS systems and gravitational wave astronomy. The pattern of fundamental physics producing unexpected applications is consistent enough to be a reasonable expectation rather than a hope. The Run 3 data, read as a whole, says that the next set of fundamental advances is close enough to measure. Close enough that the instruments of 2025 can detect the outline of something beyond the current theory. But not yet close enough to identify clearly. That is an uncomfortable position to be in scientifically. It is also, looking at the record, a productive one. In May 2026, the CERN Council meets in Budapest for a dedicated session with one primary item on the agenda: whether to approve the future Circular Collider as the next flagship project at CERN. The FCC-ee is an electron-positron collider. Circumference approximately 91 kilometers, built in a new tunnel under the Geneva Basin and surrounding terrain. First collisions projected for the early 2040s. The project would then potentially be extended, using the same tunnel, to a proton-proton collider at energies roughly 10 times higher than the LHC. The full program runs into the 2070s and costs tens of billions of euros across its lifetime. The decision in Budapest is not purely scientific. It involves funding commitments from member states, infrastructure planning across multiple countries, and political negotiations that extend well beyond physics. Whether the FCC-ee gets approved depends on things that have nothing to do with the W boson mass or the muon anomaly. But the scientific case for it was made by Run 3. The Higgs self-coupling, the parameter that determines whether the universe is stable or metastable, cannot be measured with sufficient precision at the LHC or the high luminosity LHC. The FCC-ee would measure it at a level that gives a meaningful answer. The W boson mass conflict requires a Lepton collider measurement to resolve cleanly. The persistent anomalies in electroweak precision observables need an instrument designed specifically around precision rather than energy. The Budapest vote is the field's institutional response to what the data produced. Run 3 showed that the boundary of the standard model is real, that what lies beyond it is not accessible through higher energy proton collisions alone, and that the path forward runs through precision. The FCC-ee is that path. Whether the decision goes through is a different question. What is clear is why the scientific community is asking for it. Come back to where this started. 2 detectors, 1 signal, a structure that did not have enough time to exist. Toponium is not a revolution. The standard model does not forbid it. Its discovery does not require rewriting any of the core equations. In a narrow technical sense, it is a confirmation, a measurement that found something the theory permits, in a place where the theory said the measurement could not be made. A calculation was wrong about what was experimentally reachable. The experiment reached it anyway. But sit with that sequence for a moment. The calculation was wrong, not dramatically wrong, not wrong about something exotic or speculative, wrong about something that followed directly from well-established physics that had been checked and confirmed for decades. The top quark lifetime was not a rough estimate. It was a precise number derived from first principles. The conclusion that Toponium was out of reach at LHC energies followed logically from that number. The logic was sound. The conclusion was wrong. That is what the July 2025 result actually means in context. Not that the standard model is failing. It means that a framework precise enough to predict particle masses to 11 decimal places still contains corners where the predictions turn out to be off in ways that nobody noticed until the data was precise enough to show it. And if that is true in one corner, if the calculation of what is experimentally reachable was wrong there, then the question of where else it might be wrong in the same quiet way is not rhetorical. It is the actual working question in the field right now. The machine that produced this result is shutting down. The dataset it generated is the most complete picture of matter at these energy scales that will exist for the next decade. The anomalies in it are still there. The null results are still there. The questions they raise about dark matter, about the matter-antimatter asymmetry, about the stability of the vacuum, about what determines the values of the parameters that the theory cannot explain, are all still open. They are better characterized than they have ever been, supported by better data than they have ever had, and no closer to resolution than they were when Run 3 began. Physics in 2026 knows more precisely than ever before exactly what it does not know. That is not a comfortable place to be. It is also, if the history of the field means anything, exactly the kind of place where the next thing comes from.